All right, hello everyone. Welcome to another exciting video for Calculus 1. We are moving on to section 3.9 now. I'm going to start talking about derivatives for both exponential and logarithmic functions and some applications of those. And I will tell you right now, if you are not yet having fun in with derivatives so far, this is when we really start to take this to the next level. So I hope you are ready for this because it's about to get real fun. Also, if you're not having fun, I don't understand how you're not having fun, but that's on you, not me. Okay, so mostly on derivatives of logarithmic functions, but like I said, we'll talk a little bit about exponentials. So let's look at this function, y equals ln of x. And notice they want us to find dy dx here. So sorry, I gotta pull up my notes. Here we go. So here's what I'm gonna do first, is I'm gonna rewrite this function. So we have y equals ln of x. Now remember, logarithms have to do with exponents. And first of all, one way to write this is y equals L or log base e of x, because that's what ln means. And remember, what logarithms are saying when you have something like this is what power do we have to raise the base to get the number on the inside here. So basically, what power do we have to raise e to get x, and the thing on the other side is the answer to that. The answer is y. So if we rewrite this then in exponential form, recall the exponential form of this would be e to the y equals x. So again, what we're seeing here, this is telling us that e to the power of y gives us x, which is what we have down here. Okay? And we're going to take the derivative of that function. So e to the y equals x. Take the derivative here. Notice we have both y's and x's, so this is going to involve some implicit differentiation. So we'll take the derivative of the left-hand side. Since it's e to the y, we know the derivative of that is just e to the y, but because there's that y there, using the chain rule, multiply by dy dx. Take the derivative of the right-hand side, so of the x, and that's just 1, using our power rule. Then we need to isolate the dy dx, so we'll divide by e to the y on both sides. Okay, and so what we end up with then is dy dx equals 1 over e to the y. All right, so we have not that. We have this, dy dx equals 1 over e to the y. Okay, but that e to the y was not in the function we started with, right? So we probably don't want to leave our derivative with that. And notice that from up here, from what we started with, y is equal to ln of x. So what this really looks like is 1 over e to the ln of x. And if you remember back to math 141, e and ln, those are inverse functions of one another, so they really undo each other, and this just becomes 1 over x. Okay, so these two basically cancel, just left with the x, so we get dy dx equals 1 over x. So the derivative of natural log is 1 over x. Isn't that exciting? Yeah, cool stuff, right? Okay, let's get a little more general. So that's for the case where we have an ln. Now, when we don't have an ln, this is what the formula looks like. So if you're taking the derivative with respect to x, of some just general log function, that's the derivative of that is 1 over x times ln of the base. Okay, and let's just look at how this relates to the derivative for ln. So if we're doing dx of ln of x, okay, well, notice with ln, the base is e, right? So what that tells us from this formula is that this is going to become 1 over x times ln of e. But what does ln of e equal? Remember, that's just 1, so this just becomes 1 over x. So the derivative of ln is special in that way. For any other logs like base 2 or 5 or 10, this won't happen. You'll get more this 1 over x times ln of b of the base there. Okay? And then for derivative of exponential, so you have something like the base raised to the x power. That becomes the base raised to the x power times ln of the base, which we can again do that with e. Remember, e is special, so this is only for e. So if we're doing the derivative of e to the x, well, according to this, that will become e to the x times ln of e. But again, what is ln of e? Well, that's just 1. So this comes out to be just e to the x, which is what we saw before. Okay? Good stuff. All right, so let's use some of that information to find some derivatives now. So let's say we have a function v of t equals ln of t squared plus t. So notice here, and to use our new rules or our new knowledge about derivatives of logarithms, and notice that we have a function within a function here, so we're going to have to use the chain rule, right? So you see that there's this t squared plus t inside of the function ln. So first thing I'll do here is just identify my two inside and outside functions. So my f of t here, my inside function or outside function, excuse me, looks like it would be ln of t. My g of t be my inside function, which is t squared plus t. So go ahead and take the derivatives here. So f prime of t. So the derivative ln of t, well, we just saw that's going to be 1 over t. And then we have to evaluate that. Remember, in the chain rule, you have to evaluate that at the inside function. So we have to plug in t squared plus t. So this will become 1 over t squared plus t. And we also take the derivative of the function g. So g prime of t using the power rule, that'll be 2t plus 1. And then to find the derivative of the original function, now we multiply those two. So v prime of t is going to be 1 over t squared plus t times 2t plus 1. Make the 2t plus 1. If we simplify that, we'll end up with 2t plus 1 over t squared plus t is our derivative here. Okay, so that's using our newfound knowledge of the derivative ln along with the chain rule. Fun? Definitely. Okay, let's look at another one now. So here we have f of x equals 10 to the x times x plus 3. Now notice we have two functions being multiplied. So we're going to use the chain rule here. Hopefully you all just said no. Okay, we're going to use what rule? That's right, the product rule. Okay, so let's do this. So f prime of x, using the product rule, we take our first function, 10 to the x, multiply it by the derivative of the second function. Well, the second function is x plus 3. Take the derivative of x, that's just 1. Derivative of 3, that's a constant, so that's 0. So it just becomes 1. Plus now, the second function, which is x plus 3, times the derivative of the first. So this is an exponential function. I just realized what I have in my notes I think is wrong. So the derivative here should be 10 to the x times ln of 10. Right, using what was on that previous slide. So we'll end up with then 10 to the x plus, looks like we have 10 to the x times ln of 10 times x plus 3. And you could distribute that stuff through if you wanted, but that's fine. We can just leave it like this. Okay. All right. I almost just said questions on that, which, you know, if you have questions, you can email them to me, but I guess you can't answer me because this is a video. Anyways, all right. One more thing. So let's look at this function. So we have to find the derivative now of f of x equals x raised to the x squared power. Oh boy. So here you might first think, let's take the derivative using the power rule, right? I see there's a power up here. let's just bring that down and subtract 1. But what's the problem there? Right. The power in this case is not a number, it's a function, and we haven't talked about that. Okay. So what do we do with this? Well, we're going to use logs to help us out. And so what I'm going to do is I'm first going to rewrite this function just for ease. Instead of as f of x equals x to the x squared power, I'm going to rewrite it as y equals x to the x squared power. Let's just say x to the x squared. Then I'm going to take the ln on both sides. Is that what I'm going to do? Yes. I'm going to take the ln on both sides. So do the ln of this and the ln of this, which is now going to give us ln of y equals, now remember, we have this property of logs that when you take the log of something raised to a power, you can bring the power down to the front. So this x squared can actually move out to the front of the ln of x. So we now have this. So ln of y equals x squared times ln of x. And you may be thinking this still looks a little beastly, but this is something we can handle using our derivative rules. So first of all, on the left over here, we can take the derivative of this, so ln of y, even though it has a y. So it's an ln function. So the derivative we know is going to be 1 over y, but then it has a y and not an x. Okay, in the original function, the only variable was x. So I'm going to multiply by a dy dx here by the chain rule. Equals, well, on the right-hand side, we now have two functions being multiplied, so we have to use our product rule. So we do the first x squared times the derivative of the second, which is 1 over x, plus, and I'm sorry, I ran out of room, go into a new line, ln of x times the derivative of the first function, which would be 2x. So right now our function is looking like, our derivative, I should say, is looking like 1 over y times dy dx equals x squared times 1 over x plus ln of x times 2x. Okay, so I'm going to write that all out since it's quite a mouthful and there's a lot of stuff going on here. X squared times 1 over x plus ln of x times 2x, right? That's what we're looking at. Okay, a couple things here. Notice that here we could write the x squared as x squared over 1. We have an x down in the denominator here, so I can cancel out one of the ones there. We can rewrite the other thing, the second term on the left, or on the right, excuse me. So this becomes 1 over y times dy dx equals x plus 2x times ln of x. And then we need to solve for dy dx, right, because we're trying to find the derivative. So that means I need to get rid of this 1 over y, which we can do that by multiplying both sides by y. And when I multiply the right-hand side and put it all in parentheses, so times y like that, okay, that'll cancel out the y's over here. So now what we have, whoops, is dy dx equals y multiplied by that whole thing we just had, so the x plus 2x times ln of x. And then remember, there was no y we started with in the function, right? Y was actually equal to this x to the x squared thing, so we can put that back in. So we have dy dx equals x to the x squared power times x plus 2x times ln of x as our derivative. Good stuff, right? Whew, that was fun. Okay, and last thing I'll say on this, this, again, because we didn't start with a y, we don't have to write this as dy dx, we could say f prime of x equals this. Okay? Good stuff. All right, leave it there for now. Thank you for watching.